In this video, let us take two capacitors and compare them. So the first capacitor is has nothing between the two plates, so we have only vacuum between the two plates, and this plate is positively charged, this plate is negatively charged, and we have a similar capacitor on the other side with the same dimensions, so the same area and the same distance between the two plates, but between the plates of this capacitor we have a dielectric. So if I have a dielectric, we've seen that in the last video. So let me just quickly draw the dielectric. You know that the dielectric as a whole is again neutral, because we cannot have any charge separation on it. But yeah, what we have is we have a thin layer of negative charge on this side of the capacitor of the dielectric, and a thin layer of positive charge on this end of the capacitor of the dielectric, and the central part is neutral as a whole. But we have these small layers of charges, that is due to the polarization effect. And because we have some slight we have these small layers that have charge separation, we have an electric field that goes from this side to that side. And if I have to draw the electric field of the capacitor itself, that goes from the positive side to the negative side this way, and even here it goes from this to this. And so we can see that the electric field of the dielectric actually cancels the sum of the electric field of the capacitor. Now let us have a look at the electric field in both the cases. In this case, the electric field E naught simply equals sigma, which is the surface charge density of the capacitor, divided by epsilon naught. In this case, the net electric field would be, let's call that E, simple, and that equals the electric field due to the capacitor itself, which is E naught, right, the original electric field due to the capacitor, because they're the same capacitors, minus the electric field that has been generated by the polarization of the dielectric. And because it is generated by the polarization, let's call that EP. Now if I have to simplify this, E naught is simply sigma upon epsilon naught, minus EP is sigma P, because this electric field that has been generated by the dielectric is being generated due to this thin layer of the positive and the negative charges. And so this thin layer has, if this thin layer has some surface charge density of let's say sigma P, so we are calling that surface charge density sigma P. So the electric field due to this dielectric will be sigma P upon, again, epsilon naught. And what you're left with is, we can just write this as electric field, the net electric field equals sigma minus sigma P upon, well, epsilon naught. I hope that's clear. There you go. Yeah, so we have these two things. Yeah, now one point to notice here is that, so if I have sigma here, so if the sigma or the surface charge density of the on this capacitor goes up, increases, the electric field will increase, and and because the electric field increases, the polarization of this dielectric also increases. And because the polarization increases, this difference in the surface charge density, sigma and sigma P, this difference will also increase. So we can say that sigma is proportional, rather, in other words, sigma minus sigma P is proportional to sigma. So if the surface charge density on this plate, these two plates increases, the electric field increases, and thus the polarization increases. And because the polarization increases, the difference between this surface charge density and this the surface charge density on the dielectric, that will also increase. So if I have to remove this symbol of proportionality, I'll have to put in a constant of proportionality k here. So this whole thing times k equals this. I can shift the k on the other side, and what I get is this whole thing equals sigma upon k. So now here instead of writing sigma minus sigma p upon epsilon naught, I can write that as I can replace or substitute that with this expression. So let me just remove all this to make some space, and what I'm left with is that the net electric field equals, so I can write that instead of writing sigma minus sigma p, I can write sigma upon k, and I have the epsilon naught here. Perfect. Now I have got the, if I remove this and this, now I have got the electric field in both the cases. So in the electric field in this case, E naught equals sigma upon epsilon naught, and the electric field in this case is sigma upon k times epsilon naught. Perfect. Now you have to find the ratio of the electric field in this case, where we do not have the dielectric, to the ratio of electric field in this case where we have a dielectric. What we can do is we can divide the electric field, this expression, with this expression. So if I do that, I get E naught upon E equals sigma upon epsilon naught divided by sigma upon k epsilon naught, right? I am dividing this equation with that equation. And now if I solve this further, I can write that as E naught upon E equals, so it will become sigma upon epsilon naught into k epsilon naught upon sigma. Now I can cancel the sigma and the sigma, the epsilon naught and the epsilon naught, and what I'm left with is, well, let me remove this previous step. I'm left with this expression, E naught upon E equals k. Perfect. And now if I shift the E from the denominator to that side, I get E naught equals k times E. So we are left with this expression here after shifting the electric field on this side, and what we get is, so let us just focus on this final expression here. What we are left with here is very intuitive. So E naught, or the electric field in this case, equals to k times the electric field in this case. And because the electric field in this case is less, we know that because some of the electric field is being cancelled, so the electric field in this case is less, this E is less, and we have to multiply it with some factor k to get this electric field, which is in this case the actual electric field without the dielectric. So k is some number that is greater than 1, and that tells us by how much factor does the electric field actually reduce when we put in a dielectric. So let me put this in a more intuitive form. I'll just shift the k from this side to this side, and let me just flip the equation this way and write it again. So what I get is E equals E naught upon k. Perfectly. Now E naught is the original electric field, and k tells me the factor by which this original electric field reduces when I put in a dielectric, and I get the final electric field. So k tells me the factor by which it reduces, and k is a number greater than 1 in this case. And similarly, by following the same line of thought, I can also come up with the with other equations. So we know that the equation in this case would be, so if I have to write the equation for capacitance of this case, in this case, that will be C naught equals the charge stored on this capacitor divided by the potential difference between the two plates equals to epsilon naught A upon D. And in this case the capacitance is C, some other capacitance, which equals Q upon V, which equals epsilon A upon D. What is this epsilon? Well, it is the so here epsilon naught is the permittivity of space, free space, vacuum, permittivity of vacuum. But here epsilon is the permittivity of this medium, this dielectric, this substance here, right? Because that's the difference here. So I have to write that here. And if I have to just connect these two equations, I can connect them simply by So obviously I'll skip the derivation because that will make the video very long. You can very easily derive this. So I've done it for the electric field. You can connect other factors using the same line of thought. So what I actually end up getting is that the capacitance in this case, C, equals to K times the original capacitance. Right, that is the first relation. Also what I end up getting is this epsilon naught, this or the epsilon in this case equals K times epsilon naught. So that is another relation, and just to complete it all, I'll write the original relation, which is the electric field, the original electric field equals to K times the electric field that I got here. So yeah, I'll remove this. So these are the three key relations that I think you should keep in mind. And yeah, just to complete it all, K, because it tells us the factor by which the electric field is increasing by adding the electric field is decreasing actually by adding the dielectric. So it is actually telling you the factor by which the dielectric actually affects the capacitance or the permittivity or the electric field. So this K is actually called the dielectric constant. And just to complete it all, so in this equation it is telling us that the capacitance of the new capacitor with the dielectric equals to K times the capacitor of the capacitance of the original capacitance. So upon adding the dielectric, the capacitance has increased by a factor which is equal to K, which is the dielectric constant. So dielectric constant tells me the factor by which the capacitance increases once I add the dielectric. Also, K can be written in this form, which shows me that the permittivity of that particular medium, but the permittivity of that particular dielectric is equal to the dielectric constant times the permittivity of vacuum. So right, that also makes sense. And finally, the electric field, the original electric field is K times higher than the electric field that I get when I add the dielectric. So I hope that makes sense. Obviously this is a very complicated thought, and I'd suggest you to once do all this derivation on paper yourself, so that it makes more intuitive sense to you, and try to play around with all these equations. So that's it for this video.